Welcome back, and let's give this a shot. So we are going to take a look at hydrocarbon combustion and turning this description into an equation. So the first thing we should notice is that they're telling us that we're burning the fuel butane, right? Now, we should remember from our organic chemistry during Chemistry 30 that butane has 4 carbons. So actually, this formula here is incorrect. We'll rewrite the formula together. So, meth, eth, prop, bute, right? Meth is 1 carbon, eth is 2 carbon, prop is 3 carbons, bute is 4 carbons. So we should have something like C4, and then, how many H's? Maybe some of you guys just memorize the formula. Should be that. But if not, we can always draw it out. So there's our 4 carbon parent chain, and if we think about it, we can put 4 bonds on each carbon. So let's make room for some hydrogens. Saturate these carbons with hydrogen. And how many hydrogens is that? If we add them all up, you'll notice it's 10 of them, right? Okay, so we know one of our reactants is C4H10, right? We should also know that butane is a gas. It's used in lighters to create a spark and a flame. So there's our butane gas, and it's burned in an oxygen-rich environment. So hopefully we know that, fires need oxygen to run. So we'll add oxygen gas. Now, oxygen gas isn't just O. Remember, it's O2. It's a diatomic gas. So there's oxygen gas. And hopefully we remember that every time we burn a hydrocarbon with oxygen, we have 2 products always. CO2, carbon dioxide, right? That's why burning fossil fuels releases CO2. And on top of that, we have extremely hot water, which of course vaporizes and turns to gas or steam, right? That's why water comes out of the tailpipe of cars. So there's our simple equation. Pretty easy to make compared to the double ionic one we did earlier. Okay, now let's balance this. So again, starting with an element that's found in only one product and reactant or molecule at a time. Let's start with carbon, right? Now notice that if we were to put 1 molecule of butane there, that contains 4 atoms of carbon. So that means we need a 4 here because CO2 just contains 1 atom of carbon. So we need 4 of them to take up those 4 carbon atoms. Let's do hydrogen next. We have 1 times 10 hydrogens here, which means here we only have 2 hydrogens per water molecule. So let's put a 5 there, since 5 times 2 would take up 10 hydrogen atoms. All right, moving on from there, we've got oxygen to handle. So here we've got 4 times 2 is 8 oxygens. And here we've got 5 times 1 oxygen is 5 oxygens. Whoops, 5 oxygens. And so we notice that adds up to 13. That's a problem because we cannot make 13 out of groups of 2. See how oxygen gas comes in 2? So that'd be 2, 4, 6, 8, 10, 12, 14 oxygen. We can't do that, which gives us a bit of a dilemma, but it also shows you guys something. It shows you that sometimes the best thing to do is double all of these numbers. So everything that you've put in so far can be doubled, and that's a quick trick to help you balance more easily. So let's double check everything. Now we have 8 carbons, 2 times 4 is 8, and here we've got 8 carbons, so we're good. Next we've got 20 hydrogens here, and 2 times 10 is 20 hydrogens there. So that's good, okay? Now the oxygens. 2 times 8 oxygens is 16 oxygens there. 10 times 1 oxygen there is 10 oxygens. And so that's 10 plus 16 is 26 oxygens. So we can make that by simply putting a 13 here to say 13 molecules of O2 gas. 13 times 2 is 16 atoms of oxygen. So I think with that, we can erase this extra stuff, and we've balanced our equation quite nicely. And we're ready to use it now in whatever stoichiometry questions they throw at us.